So in this webinar today, we'll go through kind of a brief introduction to some of the IoT services within Azure, as well as some of the prototyping platforms like Arduino and Raspberry Pi. To get started, a little bit about myself. So I am a senior cloud solution architect with Opsgility. I'm actually one of our trainers, so I do deliver training classes on-site and virtual when I'm not updating and building content, building hands-on labs, and recording videos that we host in our on-demand service as well. So you're kind of getting this webinar a little bit from the source of one of the people that we have who builds the content. So rolling in here, talking about IoT, we've all seen slides kind of similar to this one, where it's basically this nebulous cloud with a whole bunch of seemingly random things. With IoT, we can have everything from cars, airplanes, watches, radios, speakers, all kinds of different things, all internet connected. But really, what's the purpose of connecting these together? So if we draw some lines with these, say an airplane to a light bulb to a microscope, it doesn't really mean much. To understand the seemingly arbitrary connections that can be made, we need to first understand kind of what Internet of Things is really about first. So here's an image showing a few different kind of commercially available, consumer-based IoT products. There's obviously a whole series of industrial Internet of Things solutions and hardware platforms as well. So there's been tons of growth for the Internet of Things in recent years. This is due to a few key factors. The developer tools for programming these embedded systems have become extremely easy to use over the years. This has greatly helped reduce overall development times. The internet is pretty much everywhere, more and more as we go day by day as things expand out and get better. There's almost nowhere that you can go that you can't connect to the internet in some fashion. This allows connected devices to be put almost anywhere on the planet. Microsoft Azure and the cloud have created an ecosystem where it's extremely affordable and easy to build back-end systems to power the computing, processing, and analysis, as well as storage that's necessary for all of the data being collected by these IoT devices. This all allows for more powerful and capable devices to be built that are much smaller and affordable than they have been before. The growth of IoT has been fueled and will be continued to be fueled by the fact that these advancements in technology continue to lower the barrier to entry for building IoT devices that can be embedded almost anywhere. This kind of piggybacks on the success of the miniaturization we see in the smartphone and tablet markets as well, allowing much smaller devices. So what is IoT about? So things that we can use it for: monitoring systems and analyzing data, making future predictions based on that data and that monitoring that we do. But really the key components of why Internet of Things matters and why we need it is it allows for us to provide greater insights and make smarter decisions. So the agenda of the webinar here, we'll get into some of the architecture of IoT, so kind of general IoT architecture, and then later on we'll discuss more of the Azure services behind the scenes that kind of help fuel that in the cloud. We'll also touch on Raspberry Pi and Arduino, a couple of the prototyping platforms. So I know building industrial IoT, there's many other platforms, frameworks, things that you would use for developing those solutions. But kind of getting started with IoT, Raspberry Pi and Arduino really provide a good stepping stone to get going, kind of low barrier to entry type scenario. And then we'll also touch on Windows IoT Core, which is the version of Windows 10 that's built specifically for powering IoT devices. You can use this along with something like Raspberry Pi, or there's other hardware as well. So getting into Internet of Things architecture. So when you're connecting devices and communicating between that device and the cloud, there's what we call two-way messaging. That is a very common scenario thing that's built with Internet of Things solutions. What this two-way messaging allows is both device to cloud messaging, where we're sending maybe device telemetry, sensor readings from our devices up into the cloud, and then we're processing and handling those somewhere. And then also cloud to device messaging, which is being able to easily send a message from the cloud back down to the device. Usually this is something like a command and control message that maybe tells the device, here's an update to the firmware, I want you to update, or maybe reconfigure your settings. We don't want you to send telemetry every 3 seconds, maybe change it to every 5 seconds, maybe reset the device, things like that. So looking at a really simplistic scenario of two-way messaging, on this slide we have the cloud in the center. On the left we have maybe a internet connected or IoT based thermostat device, just kind of, again, really simple example. And on the right we have a smartphone device that maybe the user would be using. So that thermostat would then use device to cloud messaging to send messages up into the cloud. So in this case, a thermostat, the sensor readings would be things like temperature and humidity mainly. And then the consumer or user using the smartphone may have an app running on that smartphone that's able to communicate with the cloud services that are running behind the scenes, so that that user can go and see what is the current temperature, what's the current humidity, maybe change the temperature setting to control that thermostat remotely. And then that would send a message using some kind of a web API, maybe RESTful endpoint, to communicate between that device and the cloud. And then the service in the cloud that's connecting to that IoT device is then going to use cloud to device communication to be able to facilitate sending a message down to the device to go and tell it the instructions that maybe the user told it to do, or maybe if we have some kind of a cloud controlled schedule where we have timers running in our cloud service, automatically telling the thermostat to do things remotely that way as well. So with this communication, we kind of looked at the cloud as kind of this nebulous thing. We send messages to it, we get messages from it from our IoT device side of point of view. Looking into the cloud a little bit further here, with Internet of Things architecture as well as other big data architectures scenarios, the Lambda architecture is a design pattern that comes very useful. This allows you to process big data in your solutions in both of the kind of real-time fast processing data path, as well as the batch processing or slow reporting purposes, historical audit type purpose processing. So this real-time processing is referred to as the fast data path or hot data path. And this is something that would feed into some kind of real-time analysis, maybe machine learning. The system could automatically make a decision on the data that's flowing through, and then maybe even send a message back down to the device to command and control and tell it to do something in real time. And then the batch processing is the slow or cold data path. And this allows for maybe historical archiving of all of the data, or maybe an aggregate of the data. Maybe you're running a nightly batch process to build out reports or weekly reports, things like that. A little bit more, not anything that's not real time or slow processing path in that batch processing side of the Lambda architecture. And the way that this is implemented would be some kind of a message broker. In the middle of this diagram, we can see the arrows from the IoT devices going to the element marked, labeled as queues. This would be some kind of a message broker that's receiving your device messages. And then from there, it can split off those messages off to those two data paths, the fast and slow paths simultaneously. And this allows you to choose the way that you want to implement both fast and slow data processing in the single solution without having to choose one or the other. Being able to do everything that you need to do with your data within the same solution without needing to compromise, essentially. So that message queue or that message broker where messages are coming in, gather the messages in the cloud. There's a couple of architectural IoT specific components here called IoT gateways that can be used in that message transmission process or communication process. So when connecting multiple IoT devices in a solution, there can be times where connecting individual devices up to the cloud can be problematic. IoT gateways are built to provide a solution to this. IoT gateways can provide an aggregation point for multiple devices to connect through and communicate with the cloud through an IoT gateway. There's two types of gateways that can be used. So the first is a field gateway. This can be helpful in connecting low-powered or simple devices. A scenario this can especially be helpful for is maybe you have an IoT device that does not support encryption or SSL or TLS encryption. Maybe it doesn't have the processing power to do it, or the platform just doesn't have it built in. You can have your IoT device communicate with this gateway. This gateway would run on premises close to the device, and then the IoT gateway can communicate up into the cloud securely and safely without having to have that insecure device connecting directly to the cloud. And then another gateway that can be used is a protocol gateway. These are helpful in providing protocol adaptation. This can be useful when a device doesn't support certain protocols that the cloud maybe supports. So in this case, the protocol gateway could be used to translate communications from the device's protocol, maybe a proprietary protocol or legacy protocol, to one that's supported by the cloud, such as MQTT or AMQP type protocols that, say, some of the Azure messaging like Azure IoT hubs do support. And you can kind of use these in combination. You could have protocol gateways connecting to field gateways and different things in how you need to configure your solution to function. So kind of looking at more visually here, IoT architecture, kind of putting these components together. So on the left side, we have our device connectivity. So maybe we have IP capable devices. So maybe these are devices that can connect to Ethernet or Wi-Fi. Likely they support SSL or TLS. Maybe we have some existing IoT devices, other types of devices that maybe can connect to the cloud directly, or maybe they can't. So maybe we have a gateway, maybe a field gateway or a protocol gateway, or a couple of those in the mix there to facilitate the necessary communication that we need to implement. And then also we have low-powered devices that are maybe these devices that don't support SSL. Maybe they're not IP enabled. Maybe they need to connect using some other kind of hardware-based protocol to a device to be able to read the telemetry from, and then the gateway can be used as that intermediary to read the data and receive the messages from those devices, and then facilitate that communication into the cloud. And something the gateways do support generally when you implement them is the gateway normally would be kind of transparent in that transmission process. So when the cloud receives the message, the cloud knows what device it got that message from, not that all of the telemetry is coming directly from the gateway and not providing any of that transparency. This is very helpful for scenarios where you need to control and manage individual devices and the security of individual devices communicating with the cloud, and have that transparency be kind of an important piece. And then within the cloud, we have that cloud gateway that I mentioned is receiving those messages from those devices. Maybe it's sending messages down to the devices, using our two-way message communication. And then from there, the cloud gateway would be basically that message broker. It's going to receive the messages, sends them on to our backend system that maybe is implementing a Lambda architecture for real-time processing as well as batch processing of that event data and telemetry. And then beyond that, we may have applications or business connectivity to be able to offer a presentation layer. So maybe we're feeding data into something like Power BI for some visualization. Maybe it's a custom application that you built specifically for your scenario, or maybe it's even an application running on a smartphone or a tablet, mobile device that you have somebody out in the field using. So switching gears a little bit, let's look at some of the prototyping hardware for building out IoT solutions. So the Raspberry Pi is a popular IoT platform, kind of in the maker movement. It was designed originally with the purpose to help teach computer science in schools. Has a very active community building all kinds of stuff. There's lots of documentation, open source code projects and things like that that can be utilized when using the platform, so it makes it very easy, low barrier to entry. The first boards for Raspberry Pi were initially released in 2012. You can find more about the Raspberry Pi Foundation at raspberrypi.org. The Raspberry Pi 3 is kind of the most current, most powerful version of the Raspberry Pi. It sells for roughly $35 US, so it is fairly inexpensive, which is an important aspect when you're looking at kind of prototyping solutions. So it has a 1.2 gigahertz 64-bit quad-core ARM processor, 1 gig of memory. It does run that Windows 10 IoT Core, so there's a version of Windows 10 that'll run on it, as well as Linux operating systems. It has integrated Wi-Fi and Bluetooth connectivity, so that makes it very convenient to use with Internet of Things scenarios, as well as the built-in Ethernet that it has. So it's kind of a full computer on a board, good for prototyping and doing other things. Another thing in the Raspberry Pi space would be the Raspberry Pi Zero. It's roughly half the size. It's not as powerful. It has Wi-Fi, Bluetooth built in. It does support Linux OSs. It does not support, however, Windows 10 IoT Core, as it's not as powerful as the Raspberry Pi 3. There's kind of a couple different options. This is maybe a little smaller, cheaper option available as well. And then you can see in the pictures of the Raspberry Pi, there are a number of I/O pins on the board. So there's 40 GPIO pins on the Raspberry Pi 3 and the Raspberry Pi Zero. These are your connectivity point to be able to interact and connect with hardware, to be able to prototype that hardware side of the IoT solutions. So it has both 5 volt and 3.3 volt outputs. It has a number of grounds on the ground pins on there, as well as supporting a couple different buses like I2C, SPI, UART. Programming the Raspberry Pi, there's lots of resources available out there, open source in the community from Microsoft, things like that. So using Raspbian, which is the Linux flavor that is built for Raspberry Pi, you can write source code, build code using C, C++, Python, Java, JavaScript. And then you also have on the Raspberry Pi 3 support for the Windows 10 IoT Core, which allows you to use Visual Studio and the Windows Universal Windows Platform, or UWP app development tools, to build apps and deploy them out to run on that Raspberry Pi 3 device, which can make it very convenient, low barrier to entry, especially if you're familiar with Microsoft tools. There's a few starter kits available out there. One of them is the Azure Certified for IoT Starter Kit for Raspberry Pi, is sold by a company called Adafruit. This comes with, you can buy it with or without a Raspberry Pi 3. It comes with breadboard, jumper wires, temperature, pressure, humidity sensors, color sensor, photocell, LEDs, resistors, a number of components that are everything that you need essentially to get up and going with prototyping without having to basically research and figure out what hardware do I need to buy, what will work with it, how do I know if you're getting started, that kind of stuff. You can see the bit.ly link on the bottom of this slide will go to the page where you can order that from Adafruit. Some additional things that are useful with the Raspberry Pi 3 is there is the official Raspberry Pi display. It's a 7-inch LCD touchscreen. This is useful in the prototyping space as well. You don't have to have a full-size monitor you can connect. You can use that. It also allows you to kind of, if you build it in a custom case or something. And then there's also the Grove starter kit for Raspberry Pi. This starter kit does not come with a Raspberry Pi, but it's a number of sensors, an LCD screen, things like that, that work with a board that just plugs right on top of the Raspberry Pi. You can kind of see in that small picture the different components. And then there's wires that just plug into that board and plug into the sensor that you're connecting, and you don't have to worry about soldering. You don't have to use a breadboard. You don't need to really know anything about electronics, and it makes it easy to get going prototyping with that. So some kind of useful tips there with the Raspberry Pi space. So Arduino is another extremely popular kind of IoT platform or maker platform, which can be used a lot for prototyping as well. So Arduino is an open source electronics prototyping platform. So they have hardware reference designs that are licensed using Creative Commons licenses. The first boards were available in 2005, and there's many different boards available today, even a few of them that have integrated Wi-Fi, things like that are built specifically for doing IoT type scenarios. You can find more information about Arduino at arduino.cc, the URL on the bottom of the slide there. So looking at some of the different boards available, there's some entry-level boards that are not internet connected, and then there's also some wearable boards that are really small. Again, these are not internet connected. And then we have the Internet of Things boards like the Arduino MKR1000, which is a board that's kind of built specifically for building out IoT solutions. That is, the MKR1000 is pictured on the right of the slide here, and it's roughly half the size of a credit card. So you know kind of what the basic size of that one is. It's not too large. So both shown here, the Arduino Uno as well as the MKR1000, all of the Arduino boards have GPIO pins similarly to the Raspberry Pi, but they're laid out differently on the board. We can see that they're kind of how they're laid out on here with this reference diagram on the left for the Arduino Uno, which is not internet connected. And then there's the MKR1000, which has built-in Wi-Fi. And we can see actually on the bottom or back side of that MKR1000 board, it's actually marked on the board what each of the pins are. But they again have power output, grounds, a couple different bus communications that can be used, like SPI, I2C as well. And then programming Arduino, we have the Arduino IDE, which is an open source IDE. It's released under GPL licensing. It is cross-platform, so it will run on Windows, Mac OS, and Linux. And it uses a language that's kind of derived from C++, the Arduino Sketch language. So it's C syntax. It's fairly easy to program in. You can see the URL on the bottom of the slide to go to the page with information about the Arduino IDE. And so with Arduino, you're not going to be using Visual Studio and UWP development, but you would use Arduino sketches to code and program your IoT devices. And there actually is support for the Visual Studio Code editor to be able to code for Arduino as well. So you do have a little bit of an option there with IDE support. And then some additional hardware on the Arduino space is the Azure IoT Developer Kit sold by MXChip. This is actually the official Azure IoT Developer Kit sponsored by Microsoft. So it's fairly new. They just started selling it about a month ago. You can get it for about $39 US. And this board is really interesting in the fact that it has a number of sensors, buttons, a small LCD display, all built on the board, along with Wi-Fi connectivity. So it really has kind of everything you need in one board for kind of prototyping your code and cloud part of the solution without having to know very much about electronics. You don't have to solder. You don't have to figure out what hardware to get, how to get it to connect together and things like that. And then this is an Arduino compatible board. So you're going to use the Arduino IDE or the Arduino Sketch language to program it, and not the Visual Studio UWP tools. You can find the URL on here, buildazure.com. That's actually my blog. I do have a number of blog posts on there covering different aspects of this board, talking about it. So if you want to find some more information, you can find it there, or you can see there's a URL in the photo of the board and the box for it that'll actually go to the official documentation page for that board as well. So for operating systems, in the Microsoft world, here we have Windows IoT Core. So Windows IoT Core is an optimized version of Windows 10 built specifically to run on smaller devices. And it is completely free to use. You can run this on devices that either have a display connected or are headless. Headless being they don't have a display connected, they just kind of run autonomously. You plug them in and they go. It does support auto update over Windows Update. So Windows IoT Core will automatically update the device through Windows Update, which is kind of interesting. And then the hardware support mainly would be the Raspberry Pi 2 or the Raspberry Pi 3, the more powerful versions of Raspberry Pi that would support running Windows IoT Core. And then there's a couple other boards like the Qualcomm Dragon board, Minnow Board Max, and I think there's a couple others as well not listed here that do support running Windows IoT Core. So there's a few options of boards and hardware you can use with this. It's not just restricted to Raspberry Pi, but the Raspberry Pi 3 would probably be the most common kind of prototyping route. So with Windows 10 IoT Core, there's an app called the IoT Dashboard that you can download, and then this tool allows you to easily flash the SD card for your device. So Raspberry Pi 2 or Raspberry Pi 3 will boot its OS from an SD card that's plugged into the device. This IoT Dashboard will flash that SD card with the OS. You can tell it to configure a specific device name, an admin password for that device, as well as configuring the Wi-Fi SSID and password to connect to, so that once that SD card is programmed, you can stick it in your device, turn the device on, and it'll automatically boot up and connect to your Wi-Fi, so you don't have to connect a display to it to get it configured. If you do connect a display to the Windows 10 IoT Core, it will show a dashboard on that display, which does accept keyboard and mouse input if you have keyboard and mouse connected to the device. Or if you use like the official Raspberry Pi touchscreen, you can actually use the touchscreen to interact with it as well. So on the dashboard, we can see things like the device name, network information like the IP address for the network it's connected to, whether it's a Ethernet or Wi-Fi connected. And it also shows the information about the Windows 10 IoT Core version that's running on it currently. There's also some additional capabilities in here in this dashboard. There's a kind of a limited command line you can access. And then also if you click on that gear icon, you can access some settings and configurations for the board or for the device that's running the IoT Core. But the real configuration of it in a headless scenario, specifically with Windows 10 IoT Core, would be to use the Windows Device Portal. So headless management of the device, you go to the IP address of the device at port 8080, and then you can log in with that, with the login of administrator, and then the password would be the admin password you set up when you flashed your SD card. And then this will give you kind of a full web portal that you can go through and configure many more aspects of the device. You can access some debug features. You can go view the process list and look at all of the apps or processes that are currently running on the device, check Windows Update status, view the apps that are installed, install or upload apps to the device, things like that through there. Some extra control. And another app to mention is the Windows IoT Remote Client. Now this is a Windows Store app that you can download on any Windows 10 PC. And then this app allows you to basically do what would be similar to remote desktop connection to your IoT device running Windows 10 IoT Core. So you have, say, your Raspberry Pi, it's running IoT Core, it's booted up, it's connected to your Wi-Fi, the same Wi-Fi your laptop is connected to. You can run the Windows 10 IoT Remote Client on your Windows 10 laptop, enter in the IP address of your device, and you can connect to it, and then you can see on your laptop screen the display of what would display for that dashboard or the app display, even if when you have an app booted up and running. You can see what's going to be displayed on the screen that's connected to the device from your laptop or your Windows 10 PC. It can really help with development, debugging scenarios in where you maybe not in the same room as the device, or even if you don't have a screen connected to the device, but you still want to use it for development and debugging purposes. So development with Windows 10 IoT Core would be using the Universal Windows Apps UWP platform with Windows. So building basically a Windows 10 store-enabled app. Apps for Windows 10 IoT Core are not distributed through the Windows Store. You kind of sideload those through the device, but you're using the same development tools. So the same development tools, C#, XAML, many different libraries from package managers like NuGet can be included that support UWP, can be used in your app that's running on UWP on Windows 10 IoT Core. So all the same development tools that you're using to build Windows 10 desktop, Windows Phone, Xbox, HoloLens, and IoT Core devices all together. Kind of giving you one platform to build for, being able to deploy out to many different devices. On the industrial side, commercial side of things, there is the Windows IoT Core Pro version, which is a commercial version of Windows 10 IoT Core that's meant for running and distributing devices in a commercial scenario. So the free Windows 10 IoT Core, you can get up and running, building UWP apps, running on your device, prototype your IoT solutions, and when you're ready to go to market, you can stick with Windows 10 IoT Core for that product and use the Windows 10 IoT Core Pro or commercial version. So getting over back into the cloud, into the Azure services, let's talk more about Microsoft Azure and the IoT services that are available. So we have Azure IoT Suite, which is kind of the marketing name that Microsoft has given to a handful of services within Azure that they want to highlight that are built for IoT solutions. So we have IoT Hubs, which is a message communication service, notification hubs, which allows mobile native push notifications from the cloud to your mobile apps on smartphones or tablets. Stream analytics, which allows for easily implementing real-time communication, or excuse me, not communication, real-time processing of data. Machine learning, so being able to set up machine learning experiments and models and run real-time analysis on your data, or batch process data using machine learning, make predictions, as well as Power BI to be able to feed data into Power BI and easily visualize it without having to code that all yourself. So IoT Hubs is that message broker within Azure built specifically for IoT. So it's going to provide that two-way communication, cloud to device as well as device to cloud message communications. It's highly scalable. It supports millions of simultaneously connected devices. So it's much more scalable for IoT scenarios than any of the other messaging services within the Azure platform. So it provides device management and security capabilities. So you can register an individual device with IoT Hub. You can set up encryption security keys per device, even up to the scale of millions of devices, and secure the connection of each of those devices individually, and be able to revoke that connection as well individually to have that kind of fine-grained control that you need to control the security of your IoT solutions. And then there's the Azure IoT Gateway SDK, which is an SDK with Azure IoT that allows you to more easily build out IoT gateways. So like protocol gateways or field gateways can be more easily built using the Azure IoT Gateway SDK rather than having to necessarily build them all yourself from scratch. And that is an open source SDK. So IoT Hub Architecture, if you look at this diagram, it's similar to the one I showed before, but this time we're kind of looking at it using Azure IoT Hub and more in kind of Azure specific. So we still have the same devices listed on the left, so maybe IP-capable devices that can connect to the cloud themselves, existing IoT devices that maybe can connect to the cloud or maybe not, and then maybe lower powered devices that maybe have, they don't support IP connectivity or maybe they don't support encryption, things like that. And we can see some different gateways in the middle here. So we have a field gateway sitting in the local space, so on-prem, close to your devices. So your low-powered devices are connecting to the field gateway, and then that field gateway is then able to connect to the cloud, to that Azure IoT Hub. And then also we have a protocol gateway that maybe your devices are communicating through to IoT hubs as well. This protocol gateway could run on premises or it could also run in the cloud. Since it provides protocol adaptation, that could run on either side depending on what you need in your solution. So in this case, we can see excuse me, we can see existing IoT devices are maybe using MQTT or some other custom protocol They're IP enabled, they support encryption, but they're maybe not using the protocol that you need for IoT hubs. So they can communicate to that protocol gateway, and then the protocol gateway would then adapt the messages over to using, say, maybe AMQP to communicate with the IoT hubs, or in this case, what's shown AMQP-S, which is the encrypted version of AMQP. And then within the cloud, we have our IoT solution backend. So we have event-based device to cloud ingestion, so receiving messages from those devices into the cloud, maybe performing real-time analytics or batch processing, or both with a Lambda architecture. Reliable cloud to device messaging, so using IoT hubs to be able to communicate messages back down to the devices to instrument command and control. And then also per device authentication and secure connectivity between Azure IoT Hub and the cloud with those devices. So notification hubs is kind of grouped in here with IoT Suite. It's kind of on the edge of IoT Suite because not necessarily specific for IoT devices. It's more specific for things that are running on smartphones or tablets, since notification hubs is for mobile push notifications. So like those push notifications that you're familiar with your smartphone apps, like things like Twitter and Facebook, when they pop up a notification on your phone, they're using mobile native push notifications to do that. Notification hubs allows you to easily facilitate implementing those from any of your applications without having to make any code that's specific for iOS, Android, or Windows. You can use the one notification hub service, and then it knows how to send those push notifications to the various platforms, making it much easier to do. Notification hubs is highly scalable, millions of mobile devices, billions of notifications. So it is very highly scalable that you would need for big data in IoT scenarios as well. I say it's more for the end user aspect of it, not specific to the IoT devices, although there is a little bit of a caveat to that. If you have maybe an OBD2 connector in your car that's gathering device telemetry from your car's sensors for automotive, maybe that connector is connecting with Bluetooth to another device. It can't connect to the cloud itself. It's one of those not IP enabled, it's not encryption enabled type devices that can't connect to the cloud directly. In that case, you might use a smartphone as the field gateway that OBD2 connector in the car would connect to, and then that smartphone could then connect to Azure IoT Hub, send those messages to the cloud, and then maybe in that app you would use notification hubs for mobile push notifications in that type of scenario. So then that would be kind of a mixed scenario of mixing a few different things together, which is kind of why notification hubs is kind of listed in there in IoT Suite. So Stream Analytics is a real-time stream processing service within Azure. So it allows you to stream millions of events per second. So basically you have all of these events feeding into IoT Hub. You can feed those directly into Stream Analytics to start performing some real-time stream processing on that data. Stream Analytics provides a really good gateway for splitting out the data for hot and cold data paths for a Lambda architecture. So data can be input or ingested into Stream Analytics from Azure IoT Hubs. You can get data from Event Hubs or Blob Storage account. And then the data, when it exits Stream Analytics on the other side, it can output to things like SQL Database, Cosmos DB, Azure Storage, Event Hubs, Power BI, Service Bus topics or queues. And then it uses a SQL-like query syntax to kind of map the inputs and outputs of Stream Analytics together. So maybe we have an input that's an IoT Hub, and then we have outputs that are maybe Cosmos DB or storage account or something. And then we can see on the right side of this slide here, a couple sample SQL-like syntax queries that are defined for the Stream Analytics job. So maybe we have one input that's the IoT Hub data mapping to an Azure IoT Hub, and then we're outputting data for hot and cold data paths for maybe Cosmos DB on one side and maybe Service Bus queues on another. So then we can say, okay, in the same Stream Analytics job, we can run two queries to map the data. This is a very simple query. So we're saying, okay, send all the data, select all data from IoT Hub data into IoT data output. So maybe we just want to output all of our data to, say, Cosmos DB and just log it for historical purposes, audit purposes, batch processing. And then also we can say select all data from IoT Hub data into the IoT hot output. Maybe this would be the service bus queue, service bus topics, or event hubs, and then we're specifying a where clause to say, okay, where temperature is greater than or equal to 29 Celsius. So maybe we only want a subset, certain data being output to our hot path, whereas we're logging all of it in the cold path kind of scenario. Again, this is just a really simple query. There's different aggregate and temporal queries you can implement, so you can kind of get an aggregate of all the data within the last 5 minutes gets sent. So you're sending aggregates through instead of every single event that gets sent through. So there's a lot of different processing that you can do with these queries directly within Stream Analytics. And then you don't have to build that whole infrastructure to do it. You can just implement those queries within the Stream Analytics service. So looking at the Stream Analytics architecture, we can see we have maybe multiple devices sending telemetry into IoT Hub, and that data is feeding into Stream Analytics. And then from Stream Analytics, we're splitting that off for maybe hot and cold data paths, sending the data out to multiple destinations, maybe all the data or just aggregates, like I explained, to things like SQL Database or Cosmos DB. And then machine learning fits within the IoT suite as well. So this is a platform as a service predictive analytics platform within Azure. You can easily create learning models using the Azure Machine Learning Studio. You train these models based on existing data that you have. Obviously, it needs to be good, real data, not made-up data. If you use made-up data, you'll get made-up predictions. So using real data, feed in to get real predictions in your model. And once it's trained, you can output that as a web service endpoint that your application built as maybe using Azure Web Jobs, Azure Functions, other code elsewhere. You can integrate with those web services to make predictions in your solution. This allows you to add intelligence to your apps or provide insights into BI tools. And then Power BI is a platform as a service offering for being able to visualize data more easily. So again, this is one of those things where you don't have to build all the infrastructure for this visualization. You have your data, you feed it into Power BI, and then you can kind of configure these widgets to be able to visualize that data in different ways. And you can also easily embed Power BI into your own applications. So you don't have to necessarily go to Power BI to see those visualizations. You can actually embed these visualizations directly within your custom applications to kind of merge the two together. So beyond Azure IoT Suite, there's a number of Azure services that can work really well with IoT solutions. On the side of scale, real-time processing, performing actions, initiating the sending of messages from cloud to device, things like that. You could use Azure Web Jobs or even Azure Functions. Azure Functions are maybe being more built out specifically for being compatible with IoT solutions, being that it's being built as an event-driven compute solution. Azure Functions is interesting where you only pay for when your code is running, not for the hosting of the VM behind the scenes. And then there's other storage capabilities as well. You can use Azure Storage, blobs, tables, queues, Cosmos DB, SQL Database, just to kind of highlight a few of the different Azure services that would work well with building IoT solutions. Most Azure services can be used with IoT solutions. They're not all built to scale to millions of devices, billions of messages, but they all can be used depending on the needs of your solution. So it is worth investigating some of the other services to use in an IoT solution, but I would definitely start with kind of what's listed under that marketing umbrella that is Azure IoT Suite, and then kind of extending out to some of these other ones that I have listed here specifically. All right, so I have a little bit of a demo. I do have to apologize on the demo. My demo broke with the latest version of Visual Studio, so I won't be able to run it, but I'll walk through and kind of show you how things are set up and stuff with the remaining time that we have today. So say we have a Raspberry Pi device using that that Raspberry Pi IoT Starter Kit from from Adafruit. It comes with the Adafruit BME280 sensor. This is a temperature, humidity, barometric pressure sensor that communicates using an I2C bus. So we can connect this to the I2C bus pins on the Raspberry Pi board to connect it, to wire up the hardware. So we can use the breadboard to do that connection. We can see this diagram on the screen here, kind of as an example. I do have source code for this, some source code available for this specific wiring and usage of the temperature sensor here, available at the bit.ly URL and the Hackster.io URLs there on the screen. With a little bit more information about this specific scenario. And then there's also an expanded version of this that is in our Building IoT Solutions class that you'll find on the Opsgility.com site as well. So, and then we can also connect LEDs. So in this case, maybe we want to connect an LED with just one LED to the board. Instead of a diagram, I just had this short video with 2 LEDs blinking that were connected to the device. This actually uses a ribbon to connect that header board or breadboard to the header instead of connecting them with wires directly. Different options that you can do if you have, there's different hardware you can get there for prototyping. So with everything wired up, you can see I have that ribbon connecting to the breadboard, and then I have one LED and my temperature, humidity, and barometric pressure sensor connected on the device. And then also here we can see visualization of using the 7-inch touchscreen, official Raspberry Pi touchscreen connected to the Raspberry Pi to be able to have a screen connected to the Raspberry Pi with that hardware connected. And here we can see an example of it running. You can see it shows number of intervals. Right now it shows 444 intervals. The source code was incrementing that interval as it ran. Every time an interval elapsed, it would check the temperature from the sensor, send that temperature reading up into the Azure cloud, and then it would also show that temperature reading on the screen. And then with the IoT solution, what it would do is if the temperature reached past a certain threshold, it turned the LED on the device. And instead of having that hard-coded in the device, it actually used device or cloud-to-device messaging to send that message down to do that. And then also on the screen, we can see a simulated LED of a blue square on the screen just to be able to visualize that on the display as well as what's happening with the hardware LED. This is very similar to the solution that's built out in the hands-on labs that accompany our Building IoT Solutions with Azure course that we have with Opsgility. So the architecture that's used for this specific solution gives that kind of full circle of sending messages to the cloud and then messages back from the cloud down to the device after some real-time processing. So kind of going by the numbers, we can look at the red dots here first, where we have messages going from our device into Azure IoT Hub. From there, it's feeding them into Stream Analytics. And then within Stream Analytics, we're doing some real-time processing to implement a Lambda architecture. So we're sending out and archiving data out into, say, maybe it's Cosmos DB or Document DB for NoSQL data solution to store the data for batch processing. And then maybe we're doing some kind of an aggregate real-time processing on our data within Stream Analytics and then determining what data events to send out to a service bus queue that can be used for real-time processing. And then those messages that get sent in the service bus queue are then picked up by maybe an Azure function that's coded to be triggered by new messages in the queue. Azure functions would execute some kind of code. In this case, it could just say, oh, if temperature is greater than or equal to 29, then do something, or maybe it could integrate with machine learning and go try to make a future prediction based on some past aggregate of data that's being sent through. So maybe we can predict a little bit ahead of time when the temperature is going to be above that threshold, rather than being reactive and waiting for it to pass that threshold first. And then the Azure function could communicate down the IoT Hub, telling it to send a cloud to device message. In this case, like what I was describing with the images here in the demo setup would be turn on the LED, say, okay, it's past the threshold, turn the LED on. And then the IoT Hub service would then send that cloud to device message to that specific device. And then if we have many, many different devices connected up to this solution, then we could use this to be able to read all the telemetry data from many different devices and send messages down from the cloud to each of those devices specific for those devices. So I do have a little bit of code here that I will show. And first I will show kind of the setup here in Azure. We only have a couple minutes left. I think I'll focus on the Azure Components here instead. So I have a resource group here with a number of resources in here. I have all of the different components that were in that diagram. So I have a Cosmos DB account, I have an Azure function, an Azure IoT Hub instance, a service bus queue, some storage accounts to facilitate different things in here for these services, as well as a stream analytics job. So if you look at the IoT Hub for our IoT devices, I have an IoT Hub here, and if I scroll down to Device Explorer, I can view the devices that are registered with IoT Hubs. So here I have one device. I have given it the ID of that device. That's the unique ID for my device that's connected here. If I click on that, in the portal here, I can see the device ID, I can see primary and secondary keys, as well as connection strings that can be used. So then in the code that's interacting with IoT Hubs, this specific device that I've labeled as the device ID of that ID would use its own keys and connection string to connect to IoT Hub. So that device would be secured individually in its communications to and from the IoT Hub. And going back to the resource group, if I go to the Stream Analytics job, I can see the Stream Analytics job is set up here. I have some inputs and some outputs set up on the Stream Analytics. So for the inputs, if I click on that IoT Hub, I can see that it's a messaging endpoint, and I have the shared access policy and key and the name of my IoT Hub set up to configure it that it's connected to IoT Hub where it's going to retrieve the data from or receive data from as an input. And then I have a couple of outputs. Here I have an output configured to output to Cosmos DB, as well as one to output out to a service bus queue. So if I click on Cosmos DB, I can see a similar configuration where it's configured with the right keys and things to communicate with Cosmos DB. Additionally, with Cosmos DB, I have the database and collection of documents specifically that I'll be writing to. And then the service bus queue as well, similarly. And then within the Stream Analytics job, if I click on the query, this is the query that's going to map the data from the inputs to the outputs. So then in here, I have simple queries, basically the same queries I showed on the slides earlier. So we actually we're mapping from one input out to multiple outputs within the same Stream Analytics job. So we don't need a separate Stream Analytics job per mapping. We can have multiple. Here I have two. I could do more than two in here. And using this as my kind of doorway into that Lambda architecture. So I'm outputting all of the data to Cosmos DB for kind of historical purposes, batch processing. And then here, just a simple example, I'm selecting out any events where the temperature is greater than 29, say 29 Celsius. That would be, it's going to send those events out into the service bus queue. And if I go back to my resource group here, I can go to an Azure function that I have that's going to be triggered by that service bus queue. So I'll give it a moment here to load, and then I can show you the code here for what that trigger looks like. Okay, so this is my one function here. So I have it wired up to trigger. If I go to view the files, I can go to function.json, and I can view the bindings. So in this case, I have a binding configured set up. It's a service bus trigger. It can be triggered by service bus queue messages. Specify the queue name, the collection, the connection that's going to have the key to connect to it with, binding that together. And then looking at the source code for the function, I can see in my inputs, I have an input parameter string my queue item. That's going to be the string representation of the message that's being sent in. In this case, it's a string. I'm using JSON, but I could use other formats as well. And then a trace writer, which is going to allow us to log from our function. And then within here, I'm saying service client.create from connection to create a new service client for Azure IoT Hubs. And then to send that message from the cloud down to the device, I can create a new message, set some properties on that message. In this case, I'm saying setting the property LED state that I'm defining to the value of on, and then I'm using the send method to send that down to that device and then referencing the device by ID. So I'm saying, okay, send this message to this specific device. And then IoT Hub is managing the communication and security of communicating down to that device. And then once that message is received by the device, it can perform the action that it is coded to do based on the message it received. So that's all of the time that we have today. We could definitely talk about a lot of this stuff in further detail. I definitely encourage you to go take a look at the Building IoT Solutions course that we have on Opsgility.com. It goes in a lot more detail on the various things that I covered in the webinar today, as well as a hands-on lab that we have for that course. That is a pretty large hands-on lab that goes through and builds out the full solution that I kind of showed a partial kind of limited demo of.